All right. As promised, I updated this Unit 2 Learning Objective document under the Unit 2 module to include the reactions that we're going to cover in section 15 called the benzoic reactions. Some of them are reactions that you have already seen. We're just going to revisit them and explain why the new information we know about benzene enables them to behave the way that they do. Maddie?
Do you have a digital version of this guy?
No, I figured last time, only the people that came to class would get it, and then I joked, and I was like, everybody gets it. So this time it really is only the people that come to class. No, I'm just kidding. There is a digital.
Like, shoot, this is not going to look good when I take a picture of it.
Do you know what? I planned that. I rehearsed that in my head before class.
You nailed it.
Thank you.
I was going to say, we all were like, yeah.
You bought it.
Rough.
Hook, line, and sinker. No, I uploaded it here under section 15 at the bottom. And I uploaded it as a PDF. If you have issues getting it, let me know. But I'm hoping that it behaves. There's this weird thing. I make these molecules on my Mac. I copy them as like an image and paste them into a Word document. If I open that Word document on my PC, it's blurry. It's if I print it, it prints black.
Word is the worst.
And if I try to save it as a PDF from my PC, it saves blurry. So I have to save it as a PDF from my Mac in order to be able to open it well on my PC. So if you have issues, I'll try to work it out because I know it's just weird.
If you download GoodNotes for Mac, that's what I've done. It works really, really well. So just,
Okay. Good note to know.
What file type are you using?
Word, docx.
From your Mac?
Yeah. Should I save it as doc? I mean, I also resave it as PDF,
Well, I was just
which is
thinking,
portable. What is it? Portable digital file.
portable document format. So I was
Oh.
thinking the printing black sounds like a transparency issue, which I would expect from a weird PNG.
Except that some of the colors, I tried printing my functional groups table for OChem 1, and the red showed up. All of the groups that are highlighted in red showed up against the black background. It cursed indeed. So let me know if you have any issues. I'll send you over as many files as I can to try and get you one that works. But no, for those of you that want to work on there, I'm hoping today we'll actually have time to do this. Is this due? Is this graded? No. There's no submission for this. You're not turning it in. It's because I've had students in the past rightfully say, you draw so many structures on the board and I can't possibly copy them all down. So this gives you something to try and work on. I'll be honest, my OChem professor gave handouts in OChem 1, and they were all over the place. They got lost, confusing. So I think that if this is an in-class activity that works for you, that's great. And if you throw it away, that's great. If you want to hold on to it, that's great. Do whatever works best for you. I'm just experimenting with new stuff. All right, I want to start off with something similar to how we ended last class. I have an apology to make to Killian. Yesterday, last class, he put up carboxybenzene as a name for benzoic acid, which is not wrong. You can use carboxy as a substituent name for a carboxylic acid, like you can use carboxyaldehyde as a substituent name for aldehyde. But it's not common. That note that I left you guys last class, I would reiterate, which is try to name benzoic acid and benzaldehyde with all of the other groups as prefixes. So why don't we name this? And why don't we draw this structure? Oh, there was a name I didn't give you last class that I really needed to give you. So I'm going to see who knows their reading. And we'll see how this one goes. I'll explain this name otherwise afterwards.
Oh. You showed this on the board.
Yeah, it might have been up on the board, and I forgot to have you name it. Silly mistake. Very silly. But not haha funny. Weird funny. You know that one?
I know I've heard somebody say that before.
It's a meme.
From the little blonde kid who plays the kazoo.
Funny, but not haha funny. Weird funny. Yeah, Kazoo Kid?
Kazoo kid.
Mm.
Same kid.
Okay.
What did you have to say?
Name that
Oh,
on top, draw that on bottom. If you don't know toluene as a common name, this will be a good one to go put back into your list of mono-substituted compounds. And I'll explain what it is.
wait, mono-substituted?
Do you remember in our last class we looked at mono-substituted compounds and their common names? Like methoxybenzene is anisole, and hydroxybenzene is phenol. Toluene is a common name for a mono-substituted compound. So if you don't know it, I'm going to have you put it back in there early in your notes. If it's ethyl, ethoxy, benzaldehyde, meta-substituted. So meta-ethoxybenzaldehyde. Anybody feel brave enough to put their answer on the board? Jacob?
I can't remember it, but I think
You can bring your notes if you want. Do you guys know how valuable your notes are?
Sure do.
I hope you do. They're not things that I think you should do without until you can do without them, you know? Great job. The only thing I'd change about your name, Jacob, is I would remove this dash.
Oh, it's just all one big word?
It's para-methoxybenzaldehyde. Yep.
Not ether.
You could name this as an ether using functional class nomenclature, and it would have to be or benzaldehyde methyl ether. I wouldn't name it.
No, I'm deaf going with methoxy. I'm just trying to. Oh, I see ether. Good.
What do you mean? If you see an ether, call it a methoxy. Only if it's a methyl ether.
Yes.
If it's an ethyl ether, call it ethoxy. If it's an isopropyl ether, call it isopropoxy. If it's a tert-butyl ether, call it tert-butoxy.
Thank
You hear the oxy in that, right? And oxy is indicating that it's the alkyl connected by an O.
Thank you.
You bet. Anybody want to draw 2,4,6-trinitrotoluene? Draw TNT. Go boom. Don't go boom in the classroom. Don't make HCl in the classroom. No. It's a hard no, Jamie. A hard no.
You can make it.
Nope.
It's pretty easy, actually.
Nope.
It's pretty easy.
You can't. Not if I have anything to say about it.
I'll bring the necessary equipment.
What are you doing? Don't work too hard. Oh, no.
No?
No, it's benzene. Toluene is a benzene derivative. The nitros are substituents off of it. Okay, but those are not nitro groups. Does anybody want to help Killian? What makes a nitro group? NO2. Good. Now you have these nitro groups placed. You don't have benzene. Why don't you add your circle? You have them placed 2, 4, and 6 relative to a position 1. Toluene is what claims position 1. Because we're not using benzene, we're using a common name. So whatever substituent it is that makes it toluene is at position 1. And that substituent is a methyl group.
Yeah.
Great work.
This doesn't explode, this explodes?
I don't know. It's possible 1,3,5 nitrobenzene explodes, but evidently not as much as trinitrotoluene. So to clarify, toluene is one of your monosubstituted benzenes. Its name is methylbenzene, and its common name is toluene. Toluene is an organic solvent. It's used quite a bit in organic labs. We used it in our OChem 1 labs a few years ago in place of diethyl ether while we were seeking out what new solvent to use in some experiments. And then some instructors and students raised concerns saying toluene poses reproductive risks to people, so we pulled it out of the lab. Why risk it? Some people, like Raj, our instrument coordinator, our lab coordinator, say that they used to wash their hands in toluene at the end of the day to get all those organic chemicals off. And this is why chemists have higher rates of cancer than most other professions. Toluene is not something you want to dip your hands straight into. Okay, questions on the nomenclature?
Does it matter if the letter for ortho, para, and meta is in parentheses or not?
No. I think that I do typically put just the one letter in parentheses, but you don't have to.
Okay.
And in the same way, you don't have to put ortho, meta, or para completely as a word in parentheses.
Okay.
Good question. Did anybody else come up with a different name for this? I'm curious if you tried to tackle it a different way. But anisole already means benzene with OCH3, and benzaldehyde means benzene. So it's kind of duplicating a little bit too much. It almost indicates two names, or two benzenes that are linked together. I think if you called it para-anisole benzaldehyde, I would, in my head, think of this. Does that make sense? Although that probably might have a different name. So pick one common name. Benzaldehyde, unfortunately, isn't really a common name, but there's no better way to name benzaldehyde. So instead of leaning into something else's common name like anisole, name it as a substituent. Great. All right.
Actually, I have one.
Let me hear it.
For the polycyclic aromatic compounds that are linear, are there any other common names you need to know besides naphthalene, anthracene?
I will not test you on the names of naphthalene, anthracene, phenanthrene, naphthacene. I won't test you on those names. You'll never see them on material. I wanted you to see that there is a big class of them, but they just don't play as much of a role. Those of you that took OChem 1 lab here actually probably remember naphthalene from the first two experiments. We used it as an example to extract things, along with benzoic acid, so another arene member. But to answer your question, Maddie, there's so many. And so it would depend kind of on if it applies to your field or not, if you're ever going to run into them. There is actually something I wanted to show you, but I couldn't find its name even in this. This is my old research lab, and we deal a lot with conjugated systems, trying to conduct electricity between conjugated aromatic systems and metals. And so you'll find that there's a lot of systems here. This is hexahydroxy and maybe, I can't remember, triphenylbenzene? Doesn't sound quite right. No, see how that gives me 3 benzenes coming off? This is the structure I'm actually trying to show you, but I cannot remember its name for the life of me. And clearly I don't have access to that. Here's another large conjugated arene molecule. Here's that same structure again, and it's actively linked in these metal nodes. Oh, maybe I can just look up HHTP, right? Okay, well, it was triphenylene, which is almost the same as triphenylbenzene, but it's triphenylene. That's another arene. Notice how it looks kind of like phenanthrene, where it's got the 3 rings in that curved structure, but then another one on top. Equally a part of the arene family, an aromatic compound. And that's what we're getting into today. What does this term aromatic mean? Now, you all have some connection to this word aromatic. What does it make you think of?
Smells.
Yeah. Specifically, what kind of smells?
Like plant.
Yeah.
Essential oil.
Good smells, usually. Things that are aromatic, things that have aroma to them. I haven't looked into this much, but I encourage you to, and report back to me if you can. There is not necessarily a direct link between things that have aroma, those aromatic compounds, and compounds that are aromatic by definition. Confusing. Because esters are quite often part of aromas that you smell. But banana oil, which you guys are going to synthesize this semester in OChem 2 lab. Banana oil gives that Laffy Taffy banana smell, but it doesn't have any aromatic rings in it. So this term aromatic, what we should recognize that it means is an energetic stabilization. Electrons that are in aromatic systems are more stable than in their comparative systems. And it comes down to some of the characteristics. So first of all, let's look at hexatriene and compare that to what we know is not cyclohexatriene. If we were to predict the MO diagrams for these two structures, we would say that hexatriene takes 6 p orbitals from the 6 atoms, conjugates them, and then starts to place nodes inside of them with increasing energy. So this MO diagram has 6 molecular orbitals. We could call them pi 1, pi 2, all the way up to pi 6. And of course, we always plot them by lowest energy to highest energy. At the bottom, we would know that the electrons here, or the orbitals here, are all in phase. So you just get this long molecular orbital. Spans the entire structure. And at the top, what would you have? Completely in phase for pi 1. Pi 6 is completely out of phase. Every atom has an orbital on it, and it's one molecular orbital, but every atom has an orbital that's out of phase to the neighboring orbital. Imagine that if electrons occupied that orbital, those atoms would not know that they share pi bonds with each other. They each would be doing something with those electrons. It would be breaking all of the pi bonds. And then, of course, we have the HOMO and LUMO. Can you tell me how many pi electrons are in this hexatriene system? 6. 2, 4, 6, according to the MO diagram. And so those would fill pi 1, pi 2, pi 3. Can you tell me what the HOMO is? Pi 3. The highest occupied molecular orbital is pi 3, and it's true that it has 2 nodes in it. Those 2 nodes actually sit right about here, and they make it look as if there are 3 pi bonds in the system. So there's this give and take between Lewis structure and MO, remember? The highest occupied molecular orbital does kind of resemble what the Lewis structure looks like, what the bond line structure looks like. And the LUMO, pi 4, which has how many nodes? Well, you can always count. Lowest energy will have 0, 1, 2, 3 nodes. We can go in and try to predict them. It doesn't really add anything for us. Do you think that this is the same molecular orbital for benzene, cyclohexatriene? It can't be, because the structure is set up differently. Instead of having a straight chain, we actually have a circle. So the way the nodes show up, the way the orbitals interact with each other changes. According to increasing energy, we get this. Now I'm gonna draw it out, and then I'm gonna show you a shortcut for how to predict it. You know what? I'm not trying to show you anyways. Can you notice anything about that shape? It's what? It is kind of a circle. It's 1 orbital, 2 orbitals, 2 orbitals, 1 orbital. It is the shape that you make if you draw a benzene on its vertex. So for all the structures that we look at today, all semester, if they are aromatic, and we're going to define some restrictions on what makes it aromatic, you can draw that structure at a point, and every vertex represents a molecular orbital. This is called the Frost circle. And I have updated where did I update it? I did update the Unit 2 learning objectives, not just to include those new benzylic reactions, but also to include Frost circles, because I almost always have either a multiple choice question or a bonus question, number 6 now, that talks about Frost circles. A Frost circle is as easy as taking that structure, drawing it at a point, and then filling in a molecular orbital for all of the vertices. Tomato, tomato. How do you spell vertex?
T-E-X.
I am not a math guy or a language guy.
Not all science is.
Yep.
So if you did have, let's say,
isn't it? You just draw it on its side. Draw it vertically. And everywhere that you have an atom, a vertex, you draw an orbital. I've always said the same number of orbitals in is the same number of orbitals out. If you're taking a p orbital from each atom, you get 6 molecular orbitals. But they just scale in energy. It is the circular structures, the cyclic structures that change. How would you have necessarily predict that it would look like that hexagon? I don't think you would have, right? If you were in a class like inorganic chemistry, then you actually learn about group theory and character tables, and you learn more about how to predict these types of things. But it's beyond the scope of our class. But can we fill in the pi electrons? How many pi electrons in benzene? 6. So I have to fill in those 3 lowest orbitals. 2 of them are degenerate to each other. They're of equal energy. And now I'm done.
So why don't we care about like the star anti-bonding orbitals?
We can care about them.
Is it because there's like no second compound?
These up here are star pi.
I guess okay.
Star pi. Sorry, that felt weird coming out. Pi star. These up here are pi star. Anything that is above halfway is a star orbital, anti-bonding. Anything that is below halfway is a bonding orbital. Halfway is the average energy, which is to say, if none of these were connected, here's where their energy would have lied. Here's where their energy would have been.
Okay.
Hybridizing them into this conjugated system, into these molecular orbitals, stabilizes and equally destabilizes a certain number of orbitals. And then all we occupy are the more stabilizing ones. Now, it's not intuitive, and it's beyond the scope of our class to try and make sense of it. But having this design actually provides more stabilization than having this design. I wish I had an easy way to explain it. I haven't found that easy way yet. But you might notice that having 3 stacks of pi molecular orbitals is simply different than having 2 stacks of pi molecular orbitals, where 2 of them are equal in energy to each other. So hexatriene behaves like an alkene, a conjugated alkene. Cyclohexatriene does not. Another reason why benzene is called benzene and not cyclohexatriene.
Would hexahexene have more energy than hexatriene?
Hexahexene can't exist.
If it's just straight?
Hexapentene could exist. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6 atoms. Hexapentene. 1, 2, 3, 4, 5. You agree?
There's 5 bonds there.
There's 3 pi bonds, and there's only 2 other places I could put a pi bond. So I can only get up to 5. Is that not enough proof for you? Look,
Isn't that hex?
1, 2, 3, 4, 5, 6 atoms. Hex. 1, 2, 3, 4, 5 pi bonds.
Ow.
Pentene. Any other questions? So hexahexene doesn't exist. I would say this is more unstable.
Okay.
I couldn't prove it for you, but just look at it. It looks scary. So here's what we get. Actually, I think before I give you the definition for aromatic, I want to give you another molecule. I want you to look at this 5-membered ring that has a lone pair, or excuse me, that has a positive charge on one of the carbons. We can draw a frost circle for this compound. We draw it on its point, and we label a molecular orbital at each vertex. Did I say vertexes before, and that's why you got mad at me? Vertexes, whatever. And now I fill in pi electrons. How many pi electrons here? 2 pi bonds, and that positive charge, which indicates a vacancy. So 4 pi electrons. I fill them in. 1, 2. What do I do with the last 2? 1 in each orbital. Going the same direction, up or down, doesn't actually matter. Because these are degenerate orbitals, they fill equally before they half fill equally before they get a pair. Do you know what those are? True. They are unpaired electrons, which means they make their own magnets. They're also, unpaired electrons are called radicals. Do you think that this structure is stable the same way that benzene is? With those radicals, how could it be, right? Also, I do want to point out, when I'm drawing my frost circles, I'm not necessarily drawing the structure, just the polygon. I'm not putting in my pi bonds and my charge and everything. I don't need to. But here's what we get. Now, there is a reason this works. This atom up here is sp2 hybridized. Do you agree with that? We've learned about this type of atom in OChem 1 a lot. What do we call this? Carbocations. And all carbocations in OChem 1, with the exception of those produced from alkynes, 90% of the carbocations you learned in OChem 1 were just like this, sp2 hybridized. How many electron regions around them? 3. How far can those electron regions spread each other out? 120 degrees in a plane. So you get trigonal planar, flat, sp2 hybridized, unhybridized p orbital. So this is a fully conjugated system in the same way that this is a fully conjugated system, in the same way that this is a fully conjugated system. And yet this compound creates 2 radical electrons. Do you think that has a stabilizing effect like aromatic? No. And if it was not linear, or excuse me, if it was not cyclic, if it was linear instead, we know that those electrons would have always stayed paired. But because of this degenerate orbital situation, those electrons split and they become more unstable than they would have been in a linear form. And maybe I can prove that for you by drawing not just pentadiene, but pentadienyl cation. 1, 2, 3, 4, 5 atoms, 5 molecular orbitals that fill with 2 pi electrons. So it is challenging for me to tell you that this frost circle proves benzene is more stable than hexatriene. But I think you would definitely agree that the frost circle proves cyclopentadienyl cation is more unstable than pentadienyl cation. Would you agree? Can you tell me that? Yeah.
Where would you draw in the radicals on that structure?
There, you don't. That's the fault of bond line structure, right? MO theory is the only way that you can prove that this compound is not stable. Because you look at that as an OChem student, you're going to say it's very similar to this in energy. Why would it be different at all? You cannot get to an understanding of this instability, this destabilization relative to its linear form without MO theory. I could tell you and you could memorize that. We have some visitors. Do you guys feel like a zoo?
Why do it make radicals?
Look at it.
I don't know. Look at it.
I do want you to notice one thing about the hexagon versus the pentagon. This had 1, 2, 2, 1, like any good hopscotch does. This has 1, 2, 2, because it's missing one point. But we followed the frost circle. That's what its MO diagram looks like. That's not the most important part. The most important part is those unpaired electrons. So Killian, because I filled from lowest energy to highest energy, those electrons got unpaired. How could I stabilize that structure? Two more or take them out? If I take them out, I'm going to have to go from +1 to +3. That doesn't sound stabilizing. What would happen if I put into electrons? Yeah, I go from +1 to 0 to -1. That's pretty much the same as being +1. And each electron would get a pair. And it would stabilize it again.
Does the added degree of unsaturation affect anything?
That's a good question. Notice that this has 2 degrees of unsaturation, but this has 3 because of the ring. Each pi bond is 1 degree. Each ring is 1 degree. I mean, it changes the hydrogen count. But the degree of unsaturation isn't what changes its stability. It's the fact that it's cyclic. So here's what we get around this. Aromatics, to get this energetic stabilization, we follow Huckel's rules. Or it might be Huckel's rule. It's kind of like Buchner funnel. It's got that umlaut. Huckel's rules. I always think it's funny. It looks like a little smiley face. This structure must first be cyclic. If it is not cyclic, it cannot experience this energetic stabilization. It must be planar. That is to say that if the structure is large enough to bow out of a plane, then this rule is broken. And the last one, it must be fully conjugated. That means that every atom is at least sp or sp2 hybridized. You cannot have any sp3 atoms. If there's an sp3 hybridized atom in that ring, out. Not a candidate for this. If there's an atom you think is sp3 and the compound is aromatic, then that atom is not sp3, even if it breaks your rules. And we're going to have to talk about that.
So like a normal cyclohexane, you look at it from the side, it's that chair formation.
Yeah.
Benzene looks nothing like that, right? It's flat.
Benzene is flat because each atom is sp2. Yeah.
It's not chair.
Benzene can't be chair. Each atom is trigonal planar, not tetrahedral.
Would be.
There's one last rule, because I think you'll notice this structure is cyclic, it's planar, and it's fully conjugated. Every atom is sp2 hybridized. So far, this structure meets all of the rules that benzene does. Do you agree? And yet we know that this structure doesn't get energetic stabilization like benzene. It gets energetic destabilization, the exact opposite of benzene. So now we come into 2 scenarios. If the number of pi electrons satisfies the equation 4n plus 2, where n is 0, 1, 2, 3 ad nauseum. listen, you're not actually doing math here. You're just checking whether there is a way to solve this equation with the number of pi electrons. N means nothing. But if there is no whole number value of n that can be plugged in, then it doesn't work. And this is the alternative. Oh, sorry. Then the compound is labeled as aromatic.
Is n number of pi bonds or carbon?
N is nothing at all. N is a number, 0, 1, 2, 3, 4, etc. N does not relate to the structure at all.
Okay. You have an example?
Sure. If the number of pi electrons instead satisfies an equation for n, again, where n is simply 0, 1, 2, 3 ad nauseum, then the compound is anti-aromatic. Aromatic is this energetic stabilization. Anti-aromatic is this energetic destabilization. Like we saw in the cyclopentadienyl cation. I really like that name. Isn't it fun to say? You're communicating so little with so many words. I mean, with so many sounds.
It's like if you have an odd number of pi electrons or a multiple of 4.
You will not have an odd number of pi electrons. If there is an odd number, then there's a literal radical. Cameron earlier was asking, how do we draw the radicals in here? We don't. And the reason is that this resembles the HOMO of the structure. So it makes sense to draw it this way, in the same way that this resembles the HOMO of this structure. Well, no, I'm sorry, that's a lie. It doesn't resemble the HOMO of the structure. You can't.
So does that have like 2 homos then?
Yeah, technically. The 2 HOMOs are degenerate orbitals. Are you guys okay with these definitions? Aromatic and anti-aromatic.
Okay, make sure I got it. It really just comes down to these equations.
No, first follow these 3 rules.
Yes. And then what distinguishes anti from
Yep.
that is just these equations, nothing else, nothing visual.
Correct. And if you break any of these 3 rules, what do we call it? Non-aromatic. What were you going to say, Maddie?
I just said that.
Bad. No, not bad, just normal. Notice the difference between anti-aromatic and non-aromatic. They are not saying the same thing. Anti-aromatic means it has the exact opposite effect of aromatic. Non-aromatic means it just doesn't have that effect at all.
That's what I was going to ask. Is anti is the inverse?
Correct.
Yes.
Correct.
So it's
Despite following the first 3 rules.
and
They-
when you say inverse, it's the inverse effect. So instead of stabilized, it's destabilized.
That's it. Exactly.
So, octene can't octocyclo.
Octatriene, octatetrene, or just octene.
If you have an 8 carbon ring,
Uh-huh.
then it can't. Then it's anti-aromatic if it has.
We'll talk about more examples.
And Huckel's rules are just for aromatic compounds to just decide if it's aromatic or not.
Yeah, and if your compound doesn't follow those, it's non-aromatic. So why don't we look at some of these compounds that we already discussed? If you want to redraw them, that's not a bad idea. What label can we give this structure? Aromatic, anti-aromatic, or non-aromatic? Why? Not cyclic. Boom, done. I I don't care if it's fully conjugated. I don't care how many pi electrons it has. This is not a cyclic structure. It cannot get that stabilization. Benzene, is it cyclic? Is it planar? Is it fully conjugated? Yes to all of those. How many pi electrons does it have? 6. 6 pi electrons is equal to 4 times 1 plus 2. So when n equals 1, and that's what one of its allowed numbers is to be, then this equation is satisfied. Can I plug in 6 pi electrons and have it equal to 4n? I'd have to multiply by 1.5, and that's not one of my allowed options. It has to be a whole number, which means that benzene can't satisfy this equation. Do you guys see that? So because there are 6 pi electrons, then we can say n equals 1, and it solves for 4n plus 2. This is an aromatic compound. Thank goodness. Could you imagine if our aromatic ring broke the rules and wasn't aromatic?
Yes.
Cyclopentadienyl cation. How many pi well, first of all, cyclic, planar, might be hard to tell, but honestly, 2 and 3, they almost always go hand in hand. If it is fully conjugated, it is planar. If it's not planar, it's not fully conjugated. So they could honestly be linked as the same rule. They'll never disagree with each other. I mean pretty much never. I guess there are situations you could say it's probably planar, but it's not fully conjugated. And that's to say if you had like an sp3 atom, it can't bend out of plane, it's still planar. Anyways, how many pi electrons? 4. Does that equal 4n plus 2 or 4n?
4n.
So it is? Good. When n equals 1, this is anti-aromatic. And what about the pentadienyl cation? Why? Not cyclic, non-aromatic. Russ, you had another question?
I think I figured it out. So Huckel's rules says yes or no to being aromatic. Then the next step is we plug it into one of those equations and figure out if it's regular or anti.
Yes. Only thing I might change about what you said. Huckel's rules decide whether it has this energetic phenomenon. The equations decide whether that's a stabilizing phenomenon or a destabilizing phenomenon. But to be honest, you don't need the equation, it's just a shortcut. You already proved this phenomenon with the frost circles. You drew the frost circle of an anti-aromatic compound and you already agreed. Yeah, that thing is way unstable relative to its linear part. Do you agree? Huckel's rules, this equation, they just allow you to calculate it a little bit more quickly.
So does something exist where it's non-stable but still aromatic? Or is aromatic and stable kind of one and the same?
So stable is a hard word, I think, for students because people think stable means unreactive, where stable really just means requires more energy than it would otherwise. So benzene will react. We can make benzene react. But it takes more energy to make it react than hexatriene. To do a hydrogenation, it's harder to hydrogenate benzene than hexatriene. It is more stable than, but it's not like it's completely inert now.
So just like a relative scale.
Yes, it is. Relative, completely relative. Any questions? Jacob?
What if the number of pi electrons doesn't satisfy either equation?
If you have a radical,
Okay.
if you have an unpaired electron,
Okay.
then it is non-aromatic.
you wouldn't even get to the equation.
I guess you'd have to get to the equations, right? And you'd say 5 pi electrons equals neither of these, except that it gets to be non-aromatic in a different way than if it doesn't obey one of those 3 rules, correct? If I had an electron here, this MO is paired, this MO is not, I have a radical dot, not a positive charge, then it is conjugated still.
Sure.
But it is at a net neutral energy. It hasn't been stabilized like an aromatic electron would have been, and it's not as destabilized as an anti-aromatic electron would be. But it's still a radical, and what do we know about radicals? Unstable. They're still reactive. So it's just not as unreactive.
I see.
Or sorry, it's not as unreactive as an aromatic. It's not as oddly reactive as an anti-aromatic. We would expect that radical to be reactive. Going back to what Cameron said, we do not expect this to be reactive. Not the way that it is. Yeah. Hard to form, hard to keep around because it's highly reactive.
What does arene mean?
Well, arene, I think you can hear the similarity between arene and aromatic and aryl. So arene is an aromatic compound. I think sometimes arenes are, I'm not sure why they'd be used instead of aromatic, but it's just a family. I think our ACS club president has an announcement to make. Yeah. I'm just about to give them a break, so I think maybe have you give an announcement, and then we'll do a break.
Hey everyone, Alex again, bugging everybody again, sorry about that. So this is just another outreach event that we have for coming up next week. It's going to be Thursday, Friday, Saturday, which is it's another chance to get back to the community and do a couple of chemistry focused demonstrations. This is going to be, it's called KidCon. We've done this every year for the past at least 4 or 5 years. And the fun part about this is it looks great on an application, you get to do chemistry, and the best part here is you get, other people may know Comic-Con as FanX. So at the end of this, if you volunteer for a certain amount of hours, you get a free pass for the rest of the convention. And so volunteer like 2-3 hours, and then you get to enjoy yourself for the rest of the weekend. It's usually those passes are like easy $75 to $125 each. So this is just a great way to kind of bolster your application and just help out with the community and just you get a free pass. So I'm gonna be sending the sign-up sheet to John here, and he'll distribute it out amongst y'all if you like it. We have a couple demonstrations, including like our photo booth. The kids will be making slime, and there will be a couple other things like elephant toothpaste. They're relatively simple demonstrations. So it's all stuff that can be done with limited amount of training. So there's no concerns there. It's just whatever you can provide, however much time, assistance, whatever, is very much appreciated at this point.
Thanks, Alex. All right, guys, if you want to break, now's the time. Get up, move around, even if you don't want to break. Get your blood flowing again. Let's take 5 and come back in here at 6.
You make HCl.
Can you go to your other class? How did you even get to enroll in 2 classes that overlap in their time? How did you manage? Because normally it won't like.
Yeah, it doesn't let you do that. Well,
And then I have to do an enrollment exception.
physics is at the U.
Oh, that's
Do you drive up there?
It's at Sandy.
Oh, it's not close.
It's 15 minutes.
Oh, that's why you hop on the Zoom, because you take it all the way down the highway. I thought you were walking over here.
Yeah, I walked. Wait. No.
You park in
I
the
park
by
in
the
the
gym. We're in the gym. I see. I mean, I thought that you walked to the physics classrooms. I see.
That'd be nice if I could just do that.
Jamie, you may know this about me. You may not. I love teaching chemistry. Not so interested in doing chemistry, especially in my office. Not making HCl in my office, and because I like to work in there actually. And I don't want to die.
You should have heard Chris tell me about it, because like, yeah, I did that once. He was saying he did it back at his apartment at the U, and when he moved out, he had to clean dust off the ceiling. But he used ammonium chloride. He said so.
I like. What would you get out of it? What are you gonna do with it?
Yeah, this is cool. And then you could bring it back to the lab and back titrate on the malaria.
And what?
On the malaria of it through like a back titrate. This is cool to do it yourself.
Yeah, so cool. Love it.
You could dispose of evidence.
Do you remember the the 1-bromobutane synthesis lab?
How could I forget?
We reflux, but we had that tube coming over the top.
We do the same thing.
And did I tell you I had a student, a great student, just missed one small thing. He forgot to put water in the reaction flask. And what does that water do in the reaction flask? Just dilutes everything in the reaction, not in the trap.
Okay.
It just dilutes the acid and the 1-butanol. I think those are, and the sodium bromide salt. All it does is dilute things. It acts as a medium for the acid to run into the bromide, to run into the alcohol. He forgot the water, which meant it was an incredibly concentrated acidic solution, no medium to transport these hydrogen ions. And so you were creating a lot more HBr in situ than you would if it was diluted. And that HBr built up as a gas, got pumped out, couldn't be cooled by the reflux, got pumped out into the tube, down into the funnel, and into the water bath trap. Exactly like the trap was supposed to work. It was great. But he called me over and said, my tube is orange. Is that normal? No, it's not. So I ran over to look. And when you look down at the water trap, you could actually see the turbidity. You could see the wiggles. That was the HBr gas dissolving into the solution. You know, like the same way you mix any two liquids, when there's mixing, you see that. So I stuck a little pH paper in there. Sure enough, acidic, so acidic. And so we turned off the heat. We brought it into the fume hood and let it degas in there. And needless to say, I just let them use somebody else's data. I think some instructors, you know, those instructors that don't care about learning and care about, I don't know what they care about, probably would have just failed it for the lab and said, you created the most dangerous situation you could, 0. He did chemistry, just not the right chemistry. But it was really scary. It stained that plastic tube orange forever.
Why don't you just like, what if you just like left the tube off and just put it into the air? Some weird orange gas is coming off of my experience.
I had another student over the summer who joined my lab and forgot to turn on his reflux condenser. And so it condensed in the tube. And then when we turned on the reflux condenser, we turned it on. You know how those faucets are. We turned it on at full speed. And it shocked the system because obviously that glass was all very hot and the stuff inside of it was very hot. It shocked it and pushed the gas that was in the tube into the tube, which had liquid condensed in it, and shot that down into the gas trap. Actually, most of their product got pushed through the tube into the gas trap, and they got very little yield for that lab.
I thought you were going to say all the glass shattered.
Yeah.
I'm glad your lab didn't shatter. Yeah, that would have been scary.
Having something go wrong is just like nice because you think going on.
No, it's not nice. It's not. You know what the easiest lab report is? Everything went well, and here's why. And you know why? It's easy for me to grade. Yep, you're right. Good job. See you next week. You
That's
what?
what happened in our lab. Everything went wrong. I have to explain it all. Why it went wrong.
You're supposed to explain everything that goes right, too. I don't know if people know that. You're supposed to say, this worked because the acid acted as a proton source.
I'm just saying it's a lot easier to, like you said, it's a lot easier to write things than things.
Because you don't have to understand why it worked, you just have to understand why it didn't work.
Yeah.
I don't know. I have an image to show you guys with this MO theory stuff.
Do you know who made ML theory?
Mo Theorius. I don't actually, but you just let me know. I have a feeling if it was developed by just one person, it would have their name associated with it.
Straight to the code.
Say it louder. Oh, I thought you were saying if it was made by a woman, it wouldn't have her name on it.
Yeah, that's something.
Yeah. Probably true.
Robert S. Mulliken.
Emolican. Oh, no, it's MU. Shoot. Well, I'm surprised it was just one guy. Mulliken sounds really familiar. Oh, Mulliken. I just taught about him in my Gen Chem class. Mulliken determined the charge on an electron and the mass of an electron.
Oh, how did you?
I didn't think MO theory was that old, actually.
1940s.
Maybe I'm wrong. Anyways. Okay, I'm trying to show you guys something, but it's not behaving. If you head to our modules, under our Unit 2 module, you will find this Section 15 PDF. And it's a PDF rather than a PowerPoint because I used to give these to students to write down things. And then I stopped going off of these. But there is an image on one of these slides that shows you not the not the frost circle of benzene, but its MO diagrams. Notice that the bottom molecular orbital is completely in phase. All of those orbitals are aligned completely. If this were done more technologically advanced, they would all be connected to each other. It would be one donut on top and one donut on the bottom. What do you notice about the next two orbitals? The degenerate orbitals. What do they have in common?
I have two out of phase.
They have two out of phase.
I know. Interactions.
There's a node. Is that what you're going to say, Jordan? They each have one node, which is what we expect. Every time you go up an MO, you add one node. The highest energy molecular orbital has the most nodes. You can literally just count the nodes and map out their energy. The two degenerate orbitals have the same number of nodes, but what is different about those nodes? The way they move through the ring. This structure on the right, and I think this is where you were second guessing yourself, I have a typo. The top lobe should actually be flipped relative to the bottom lobe. They should be out of phase, but actually as they are, they're in phase, and that's not how it's supposed to be. The MO on the right cuts through two atoms. You'll notice that there's a nucleus at each p orbital, and there's a missing two atoms. So this was one of your pre-reading questions, which was when a node cuts through those two atoms, the electrons in that orbital are never found at those atoms. And that actually looks a lot like two pi bonds, or just one pi bond on either side. So there are some reactions that we'll do this semester where we can probably predict the electrons are leaving from that orbital specifically. Jamie asked this earlier. He said, can you know which of those two orbitals it reacts from? Kind of, actually. Based on how it behaves, you might be able to say it's the orbital on the right. The orbital on the left doesn't cut through atoms, it cuts through bonds, and so all of the nuclei have some experience with the electrons. Move up to the next degenerate set. What do you notice? They both have, yeah, two nodes. They both have two nodes. Once again, going in different ways through the structure. The one on the right are perpendicular to each other. The one on the left are perpendicular to each other. But those two sets of perpendicular nodes are at different angles relative to each other. And then you get up to the highest orbital, and you'll notice that there are three nodes. Each atom is out of phase with the other atoms. And we can also do this. We can look at a more rigorous structure or a demonstration of these orbitals. Even this isn't necessarily the best because they're still kind of showing them as those p orbital blobs. But you blend them all together. It's just one donut on the top with that donut on the bottom. There's this really cool thing that happens because of the electrons there. If you induce a magnetic field perpendicular to that ring, do you know what happens to electrons that are in a circle with a perpendicular magnetic field?
Doesn't depend what direction.
Electricity. They move. So if you put benzene or any aromatic compound into a magnetic field, you can induce that circular movement of those lowest MO pi electrons. Do you know when chemists put benzene or aromatic compounds into a magnetic field? We've talked about it.
Maybe like a mass spectrometer or something?
Bailey, what are you thinking? Any idea? Mass spec is in a magnetic field, but it's also charged fragments that are there. And so there's more of an effect of the charged fragment. On that train, though, stay on the train of spectroscopy. NMR uses a magnetic field to align the nuclei inside of the molecules, the proton nuclei or the carbon-13 nuclei. It uses a magnetic field to align them. So you induce a magnetic field anytime you're subjecting an aromatic compound to NMR. So because of that, the electrons in that ring start moving around. That has this propagating effect that de-shields the nearby hydrogens of their electrons. And what happens when a proton is de-shielded? When its electrons are pulled away from it, it encounters the magnetic field more, it's offset from its ground state energy more, and it releases a higher frequency resonance frequency. So it gets picked up further to the left. Students ask this all the time. No, they don't. I say this all the time. Why is it alkane protons show up very far to the right, very shielded? Protons near an oxygen, like on that ester, show up towards the left because they're de-shielded by the electronegativity of the oxygen. But protons that are by an aromatic ring show up even further left. It's just carbon. It's not like there's any electronegativity pulling on those electrons nearby the hydrogens. It's this induced movement because of the MO diagram, because of that lowest molecular orbital.
Because they're spinning around towards the magnet? Like
Because the magnet makes those electrons spin, and because of that, there's this de-shielding effect from the nearby hydrogens, the aryl hydrogens. Isn't that cool? And I feel like it just all comes full circle at that point. And obviously, I didn't have you write anything down for that because I don't like essay questions. So I'm not going to ask you to explain why and how aromatic hydrogens show up so far downfield. But for any professor that says MO theory doesn't have anything to offer us in organic chemistry, I beg to differ. I think MO theory explains everything. It really does. All right. Now, we're going to move on in this topic of hybridization, and this is where our sheet is going to become handy in a little bit. We're going to look at what happens with other rings that have charges beyond just the cyclopentadienyl cation. We're going to look at what happens with nitrogen and oxygen in the rings in heterocyclic structures and O-heterocyclic structures. First, let's look at charged carbon species. If you don't feel like you have the energy to copy all of these structures down, then just pay attention to the trends that we're looking at. And if you struggle with your 7-membered ring, I'm going to demonstrate it for you. Kind of like benzene, you start your 7-membered ring out with just those 2 lines, but instead of horizontal lines coming down, you've got 2 more lines that still kind of come out a little bit, and then 2 more lines that come in before you get 1 flat line at the bottom. Cycloheptane. And for this structure, we're going to have cycloheptatrienyl cation. I'm sorry, guys. I kind of made a mistake up on my cyclopropenyl ions. I wanted to have plus minus, plus minus, plus minus. Notice here with your cycloheptatrienyl ions that you've got the vertex at the top and then alternating double bonds. Okay, maybe this was a bad title, actually, because they're not all charged carbon species, are they? The ones on the far right are not charged. What trends do you notice in these molecules? There is a charge trend, and there's also charge not trending in some ways. Do you notice anything? Could you put words to it? Yes.
Kind of just the even cyclic structures are more kind of uncharged. Or
Yes.
Not uncharged, but they don't have a
No, you're right.
sign charged.
They are uncharged. They don't have a charge. When you have an even number of carbon atoms, there is no charge. When you have an odd number of carbon atoms, there is a charge. That's the trend. And when you have an odd number of carbon atoms, then your charge can either be positive or negative. Can we agree that all of these structures are cyclic? So rule number 1 from Huckel's rules is met. Can we say which of these are planar? How about cyclopropenyl? You guys hear what I'm saying there? Cyclopropene, but it's a cation, so it's the cyclopropenyl cation. Planar?
Yeah.
It is forced to be planar. It has no choice. In order to have that bond angle in that 3-membered ring, it must be planar. What about fully conjugated?
There are no sp3 atoms.
There are no sp3 atoms. This cation is sp2, and the alkenes are sp2. So how do the pi electrons work? Is it aromatic or anti-aromatic? How many pi electrons? 2. So which equation does it meet? Killian says it meets aromatic. Would you agree? When n equals 0. What does n mean? Nothing. It means nothing. Okay? It's just a solution. You draw a Frost circle for this, what are you going to get? 1 orbital on the bottom, 2 orbitals on the top. The pi electrons only go on the bottom. No radicals. This compound, surprisingly, is aromatic.
So, and it's just whatever satisfies.
And is whatever you can use to satisfy either of those equations. You'll only be able to satisfy one of them.
Just there to show that there's a
That's right.
Is there a radical on the top?
I spent ages looking
No radicals here. The MO diagram, again, draw it at its point, fill in the pi electrons, that's it.
But the pi's at the top.
You draw it on a vertex, that was one of our rules. Draw it on a vertex, draw an MO at each vertex. You can draw this structure, you can draw all these structures. Like that. Does that remind anybody of anything?
Harry Potter?
The Horcrux. Or what? A traffic sign, yeah. Yield to positive charges. Yield is upside down, isn't it? Why do we draw it like that? Because it's aromatic. Those electrons are delocalized. They're not at any one carbon atom. They're at all of them. And there is a positive charge. Do you remember the other day I asked how many electrons in the circle benzene? And you all said 6. How many electrons there? Not 6. I hope. Only 2. But that positive charge, again, actually gives us some inclination or something to work with for that. Now, what might you say about the cyclopropenyl anion?
It's full pairs.
I disagree. What is this negative charge? It's a lone pair of electrons. So if it helps you, draw in that lone pair of electrons. What hybridization would you expect this carbon to have? You should expect it to be sp3 because the carbon has hydrogen, lone pair, carbon-carbon bond. That's 4 electron regions. There is an issue though, which is this carbon is squished. It cannot get out of being conjugated. It would like to be, but it doesn't have the angle freedom to become to not be conjugated. So against our better wishes, that atom is conjugated, which means it satisfies all of Huckel's rules. I will say this, most instructors, when they ask questions like, is this compound aromatic or non-aromatic or anti-aromatic, they will say, assume all structures are cyclic, planar, and fully conjugated, so that you don't have a choice about getting out of that. But there is an actual rationale, which is this has no choice. So if I take my cyclopropenyl cation Frost circle and I add 2 electrons, 2 radicals, destabilized, anti-aromatic. If we had worked with the assumption that that carbon was sp3 hybridized, then we would have broken this fully conjugated rule and we would have said non-aromatic. But that structure does behave anti-aromatic. It doesn't have a choice. Cyclobutadiene. Is it cyclic? Is it planar? And is it fully conjugated? It is. Pi electrons satisfies which equation? Anti-aromatic. This is an anti-aromatic compound. In fact, it's so anti-aromatic that it does everything it can to avoid being anti-aromatic So in actuality, this structure looks a little bit more like this. Do you see the, well, I guess I'm not trying to confuse you by where the pi bonds are placed. It looks a little bit more like this. Do you see the difference? It stretches itself along the sigma bonds, which means that the p orbital here, which is conjugated in the pi bond, cannot conjugate to the p orbital here. It's too far away. So it does everything it can to break itself out of being fully conjugated to become what? Non-aromatic. Cyclobutadiene is an anti-aromatic compound that stretches itself to become non-aromatic.
So is there like a distance that makes it non-aromatic? Like there comes a point like
When the orbitals are too far away to overlap.
okay.
Breaks, that's the definition of conjugation, is that the p orbitals are all overlapping. So when it stretches those sigma bonds, the p orbitals get too far away from each other to overlap.
I guess my question then is, do we just assume that all of those little square guys, are going to just be non-aromatic, or do we treat them like they're anti-aromatic?
This is where you would need to rely on me saying, assume all structures are cyclic, planar, and fully conjugated. Yeah? But I don't want to just give you guys what the textbook says. I want to give you the fun answers, the real life structures. This structure is anti-aromatic that does everything it can to become non-aromatic. Because what's more stable than anti-aromatic? Non-aromatic. All right, cyclopentadienyl cation. We already know this.
More stable?
Non-aromatic is more stable than anti-aromatic. This cation, what is this? Anti-aromatic. We looked at this as one of our first ones. So what is going to happen when two more electrons are added? Remember that this is a lone pair. That negative charge means carbon has a lone pair. Now this is where someone might come back in and say, that carbon has 4 electron regions. Which means it wants to be sp3 hybridized. I told you guys why atoms become sp3 hybridized. Why do atoms take on sp3 hybridization?
Repulsion.
To minimize repulsion. They sp3 hybridize to get their electron regions as far away from each other as possible. Because sp2 hybridization leaves a lone pair in a p orbital, which is 90 degrees away from all the other pairs. Whereas sp3 becomes tetrahedral, everything is 109 degrees apart. So sp3 hybridization is meant to stabilize. What's more stabilized than being aromatic? Nothing. So what does this atom need to do in order to get that aromatic stabilization? It needs to leave the lone pair in a p orbital. It needs to stay less hybridized, defeating our typical rule. We typically say, count the electron regions, that's the hybridization. Unless there's a chance for aromaticity. This compound is aromatic, and because of that, we know that this carbon is sp2. Where is the third p orbital? The lone pair has it. The lone pair is in that p orbital that is not hybridized, and that's what allows for full conjugation. Do you see it? No? Typically, this lone pair on a carbon wants to be sp3 to minimize its repulsion and to become more stable. But being sp3 would mean that this compound is non-aromatic. Whereas being sp2 means every atom is sp2 hybridized, cyclic, planar, fully conjugated, 6 pi electrons, 2, 4, 6. If and only if this carbon doesn't become sp3 hybridized. If and only if this carbon breaks all of our rules. So are you comfortable breaking the rule you learned in Gen Chem to determine hybridization? If and only if it allows for stabilizing aromaticity. I know that I'm probably the first one to tell you that you're putting a hybridization towards something to stabilize it, but that's why you've been doing it your entire lives. It's to minimize strain, it's to minimize repulsion, it's to get more stability. But aromaticity provides more stability than that alone. So now we throw out that rule. If it can be aromatic, forget the rule.
So if we're already in the category of being aromatic, is that relatively less stable compared to other aromatic things?
No. No, cyclopentadienyl anion is very stable. It can actually be sandwiched into a compound called ferrocene, where iron binds to 2 of them like a sandwich. Actually, we're going to look at ways to make that compound. And we'll talk about how it's much easier to make than relatives of it because of its stability. So let me ask you this again. If this lone pair was in an sp3 orbital, would the compound be aromatic? The compound would be non-aromatic. If this lone pair is in a p orbital, is the compound aromatic? Yes, it is. So maybe I can clarify this. Rather than putting sp2 here, what I'm going to show is that this lone pair sits in a p orbital, just like all the p orbitals of the ring, fully conjugated.
So it's in a p orbital, just an unbonded p orbital.
It's actually not unbonded. The word we want to use for it is delocalized. Does that make sense? It is part of a bond. Bond line structure screws us over. Look at the MO diagram for it. That's so terrible, but you get the picture. 2, 4, 6 pi electrons. One of these has to be that lone pair. Which one is it? I don't know. Because it's not a lone pair. It's part of a molecular orbital. It is delocalized over the whole atom.
In the same way that resonance is.
Yes, it is resonance. So you can show this resonance structure, Russ. Lone pair in, lone pair out. This resonance form shows that the negative charge is on the next atom. You can show 5 of these resonance forms where each carbon holds the lone pair. So rather than showing it as 2 double bonds in a lone pair, similar to rather than showing it as 3 double bonds, just a circle, because they're all in a pi bond with each other, according to the MO diagram, and a negative charge, because there is an excess of electrons.
Wouldn't unhybridized be the biggest or the best descriptor for the lone pair? Most important
No,
thing?
the lone pair is not on that carbon atom. It is in a p orbital, but the lone pair is not on that carbon atom. It's on all of them. So we say the lone pair is delocalized.
Does that mean, so you have 5 possible locations of it.
5 total.
Are there any intermediates where it's like the dashed bond? Are there any intermediates?
This is what you're talking about.
But will it always look like that, whichever
It looks like
direction?
this. It doesn't look like this.
It's just switching too fast?
It's not switching at all.
Delocalized too much?
It's delocalized. not too much. It's just delocalized. It doesn't, that lone pair does not belong to one atom. It's not one atoms. But bond line structure won't let us draw it any other way.
So bond line would say that when it reacts, it like stops, reacts, and then it just randomly gets stuck there. Is it ever?
Yeah,
is
at
it
some
ever-
point it will react from one carbon. How do you choose which carbon? In this structure, you don't have to choose. It's any of them. They're all identical.
In bond line, would you make a dash or something around it to show that you? Okay.
You just wouldn't show it in this form. In the same way that if you're going to show benzene reacting, you don't show it with a circle. You have to show the electrons. Like I said, MO theory, MO doesn't work great for showing electron movement, but bond line doesn't work great for understanding electron placement.
Is it fair to say that that's like 90% of the benzene? Like you're almost there. It almost behaves like it is benzene.
I mean, it's aromatic in the same way that benzene is. Yes.
Okay.
It just has less carbons and a net negative charge, so it can be pulled by a magnetic field like a mass spec. Okay, what about benzene? Thank God, let's move on. Cycloheptatrienyl cation. What do you think? Six electrons, just like this, just like this, just like this. Compare that to 4 electrons, just like this, just like this, just like this. These are just changing how many carbons are in the ring. And in a similar way, this is basically benzene, but of a 7-membered ring, except that it has a charge, so it does give it different reactivity than benzene. But compared to a 7-membered chain with a positive charge, this is more stable. And we don't have to worry about hybridization because a carbocation already is sp2 hybridized. So we are confident that this is always following Huckel's rules. What about the cycloheptatrienyl anion?
Is the lone pair in the P shell?
That's a good question. So if we follow the rules and say, assume that this is fully conjugated, I don't necessarily want to erase this stuff, but it's in the way a little bit, so I'm just going to box some of this off. In the same way that we've been drawing these other ones, we can show this like this for the anion. Or we can show it like this for the cation. Those charges are delocalized. If we say it is cyclic, planar, and fully conjugated, then it'd be anti-aromatic. However, it may try to become non-aromatic. How would it do this? How can this high-energy anti-aromatic compound try to become non-aromatic? Good. It's going to try to hybridize that lone pair into an sp3 orbital. So I'm going to say lone pair, LP, in sp3 orbital. That's what it's going to try to do. Whether it's successful at that or not, don't know. But do you know about carbanions? Are they stable inherently? Well, they're already very reactive. So this compound has both a very good base or nucleophile, and it's trying not to be anti-aromatic. So if it does get to be sp3, it's still very reactive. It's just not as reactive as before. But if the lone pair is in a p orbital, if the carbon is sp2, if the structure is fully conjugated, that makes it anti-aromatic. All right, what about cyclooctatetrene? If we're following the rules, this compound is anti-aromatic. But cyclooctatetrane exists, is stable, not inherently destabilized. So in actuality, this compound stretches. We say that it forms a bowl. I'm going to draw it over here for us. In the same way that cyclobutadiene stretches itself, cyclooctatetrene folds up or down, whichever way you want to see it, and it forms this bowl. And the reason I turned this back on was because I want to see if I can find a way to give that to you. Oops. So what does it break now of the rules I just erased? It's not planar. Oops. I did a good job, right? I did all right. It's hard to look at. Look at this structure on the bottom. That version of cyclooctatetrene. Doesn't that kind of remind you of the first time you saw cyclohexane? It looks from the top-down view like it's flat. Cyclohexane looks like it's flat until you actually see its 3D model and you find out that cyclohexane is a boat. It's the same thing with cyclooctatetrene, where it looks flat from the top-down view, but it is actually quite bowl-ish. Now, cyclooctatetrene is a very cool thing. Actually, I think I worked with cyclooctadiene, which also forms kind of this bowl shape. And cyclooctadiene will sandwich nickel ions. So you can have nickel pi bonding with the alkenes on top and on bottom. It forms this little sandwich. Very cool stuff. So here's the deal. If I ever give you a question with these exceptions, I would have to preface it by saying, assume that the structures are cyclic, planar, and fully conjugated. Don't assume they behave like they actually do. Or, more likely, I'm going to give you real structures that don't break the rules. And 9 out of 10 compounds in this family are aromatic because there's just inherent stability to that as opposed to being anti-aromatic. All right, what do you guys think? Interesting? We haven't quite gotten to what we have on that sheet yet, and that's because I want to look at nitrogen and oxygen species. Now I'm calling these nitrogen and oxygen species, but they're more often referred to as N-heterocyclic or O-heterocyclic structures. To be honest, I've not heard much of, I don't know that I've ever heard O-heterocyclic. I think I may have invented that today for the first time. N-heterocyclic structures are a huge component of pharmaceutical drugs. Something like more than 70% of pharmaceutical medicines have N-heterocyclic structures in them. Not necessarily aromatic structures, but N-heterocyclic structures. They have a nitrogen in the ring. So this is a big, big family of molecules. Now I want to take this aromatic compound, cyclopentadienyl anion, and I want to swap it for a nitrogen and an oxygen. Here's what I'm going to tell you. Oops, I did forget something with that nitrogen. he needs a hydrogen. I'm going to tell you that these atoms, or these molecules, are aromatic. Because they are. In fact, they're both on your sheet. On the left middle, you'll see pyrrole. It's kind of fun to say 'cause it's got that double R. I don't know. I don't think you actually pronounce it. Pyrrole and furane. Furane is actually the second from the top on the right-hand side. You all know furane's little brother, tetrahydrofurane, from all of your chemistry reactions. You learn about THF, that's tetrahydrofurane. Furane, pyrrole. If these are aromatic compounds, what does that mean about the number of pi electrons present? There must be 6. It can't just be these 4 pi electrons, because that would make it anti-aromatic. Where does the 6th, where does the last set come from? Lone pairs. If these are cyclic, what does it say about the hybridization of nitrogen and oxygen? Would you call them sp2 before today's class?
No.
You would have called them what?
sp3.
Why?
You gotta get the biggest distance between them.
4 electron regions. Spread out those electron regions as much as you can. But now you recognize that if you do that, you cannot have aromaticity. So in order to get aromaticity, you forsake hybridization for better stability, aromaticity. So this atom here, sp2. This atom here, sp2. Can you tell me the nature of this carbon-nitrogen bond? According to valence bond theory, which is like what orbitals are overlapping. Yep. sp2 and sp2. The sigma bonds are always an overlap of the hybridized orbitals. This is sp2 to sp2. What is this? sp2 to sp2. What is this? S to sp2. What's the only orbital left for nitrogen's lone pair?
P.
P. The unhybridized p orbital. What does that p orbital do then? It delocalizes it with the rest of the ring. So this lone pair up here, I'm going to draw it in red. This lone pair is delocalized. It is not localized to nitrogen. That means, just like this, you can draw 5 resonance forms. And you will see the lone pair pop up on each of those 5 resonance forms.
So if something's aromatic, is it true that we're basically trading hybridization for delocalization?
Correct. You are trading hybridization of the atom for delocalization of the lone pair. How many lone pairs does oxygen have? How many of the lone pairs are delocalized?
Wow. Apparently just one.
Because if both were delocalized, then the aromaticity would not be met. And also, if both of them were delocalized, it would mean they're both in a p orbital. So let's walk this through again. What is the nature of this bond? Do you know it, Luis? sp2 to sp2. And this bond? sp2 to sp2. Where is the other sp2 orbital? Nitrogen used its third one to go out to hydrogen. Where is the other one here? One of the lone pairs. You guys are getting it. I'm going to draw that in here in black. One of the lone pairs is localized in an sp2 orbital. Where is the other one? delocalized in a p orbital. Here's what that looks like. Again, taking you to that PowerPoint PDF called section 15. And this time I'm scrolling all the way down to the bottom. Because your textbook has this great image of what this looks like side on. Here's furane. There is the localized lone pair in an sp2 orbital. If it were nitrogen, it would be a bond out to some other group. And there's the delocalized in the p orbital. They can't both be delocalized. They both have to be in one p orbital, and then there would just be an empty sp2 orbital, which doesn't make any sense. So they can't both be delocalized, only one can be, physically. And when it is delocalized, you get aromaticity. Mm-hmm.
Theoretically, if you had sp on the oxygen instead and two p orbitals, what would the direction of the second p orbital be?
It would be the plane of the ring, which would not conjugate with the other p orbitals.
Perpendicular.
They'd be perpendicular to all the other p orbitals.
And would the pentagon be squashed more?
It would not be in a favorable spot, yeah. Okay, to wrap this up, there is two other situations that you can find these compounds in, and that is when they are double bonded inside of aromatic structures. I have intentionally missed something from one of these structures. Where? How'd you know that? 3 bonds to oxygen means that this is a positively charged oxygen. What are the hybridizations of oxygen and nitrogen? This time it's not a trick. How many pi bonds do they have? They both have a pi bond. So what hybridization do they need to be in a pi bond? sp2. So there's no trick here. These are sp2 atoms. So tell me about their lone pairs, because this time they both have the same number, 1 lone pair each. Are their lone pairs localized or delocalized? Do you have a question or you want to answer? Tell me. How do you know?
Because of the pi bonds, basically, as I think of it, is like they're sp2, so we have 3 things, 3 planes held by the lone pair, and then the bonds on each side.
Good. Here's how I would say it, just repeating it another way. sp2 orbital, and p orbital. P orbital's already consumed, can't put a lone pair in the p orbital. That's how a p orbital, or excuse me, that's how a lone pair gets delocalized. It gets sat in an unhybridized p orbital. P orbital's taken up. sp2, p, what's the only orbital left? sp2. Cannot be delocalized. It's not in conjugation. It's not in the p orbital. sp2, p, nothing left. It can only be in an sp2 orbital. By the way, this structure here is called pyridine, which is a very common organic base. If you don't want to add water and hydroxide as a base in a reaction, pyridine's your guy. So I might encourage you to think about the 2 ways that nitrogen shows up in aromatic structures. Pyrrolian nitrogens, which look like normal nitrogens but are actually sp2, and pyridinyl nitrogens, which are already double bonded. Delocalized lone pair in pyrrolian, I'm making up these words. Localized lone pair in pyridinyl, but they sound like real words. One delocalized lone pair in furanyl, furanian, I think furanian sounds better. Furanal sounds like a, never mind. Localized lone pair in anthrocyanine, anthrocyanal. This is a very common structure. I have a anthrocyanin structure down here on the bottom left. You'll notice that positively charged oxygen in there. That is a very common structure that gives color in like blueberries and violets.
Which one?
The anthrocyanin structure.
Oh.
They might seem confusing at first, but when you go through this, here's what I want you to do with this activity. Draw in all the lone pairs for nitrogens and oxygens in the ring. You can ignore atoms that are outside of the ring. Decide if those lone pairs are localized or delocalized. To do that, assign the atoms as sp2 or sp3. That means that you're also analyzing whether the rings are aromatic or anti-aromatic or non-aromatic. We have a little bit more to touch on with aromaticity next week, Tuesday, and that is some of these structures that are polycyclic. So we're going to talk about polycyclic structures. We've been talking about charged carbon, nitrogen, and oxygen. We'll talk about polycyclic, and that'll bring us into learning about benzylic reactions from there. You got a question?
Are they aromatic?
You'll have to find out. Anthrocyanin?
No, those two.
Oh, these are aromatic. Yeah, we know they're aromatic. They're benzene, but with a heteroatom. They're aromatic compounds. All right, thank you guys for your time. I apologize for taking you over. Have a great weekend, and I'll see you on Tuesday.